Welcome to this brief graphing tutorial here for Chem 108, the Density Lab Part A. We're going to take a look at how you can actually put together a graph to visualize the trend of mass as it corresponds to volume. Here we've got some data involving the element antimony and the mass and volume of three separate pieces of them. And we're going to see how to visualize this using graph paper. And so what we're going to do, first off, is take a look at the properties and the units here and put those onto our graph. So what we're going to do, since we'd like to calculate density, which is mass over volume, our goal is going to be to make the slope mass over volume. So that means mass needs to be on our y-axis and volume needs to be on our x-axis, since slope is going to be delta y over delta x, rise over run. So if I bring my graph paper in here, what I can do is graph on one side here mass, and I want to label what the units are because all I'm going to be able to read off are numbers, and then on the bottom volume in cubic centimeters. So that at least gets us started. The next thing we need to do is take a look at the actual data that we're going to be trying to graph, because we'd like to use as much of this surface as we possibly can. So, taking another look here at the numbers, we'll notice that for mass, it goes up to 68.47 grams. So 0 to 70 or something like that would allow me to use the entire graph. For volume, it goes from about 0 or somewhere near 0 all the way up to 10.1. Now, at this point, we're going to take a look at our data and try to put it onto this graph. So each pair of pieces of data, a mass and a volume, are going to correspond to one data point. And we'll get that by finding the volume first on the x-axis and then moving up to our mass. We have these 3 points that are going to indicate to us the trend. And you'll notice that in actuality they seem to lie pretty nicely on a straight line. To determine the slope of that line, we're going to actually need to draw it. And to accomplish that, you're going to need a straight edge. Now, I'm going to place one here that's going to put most of this in shadow. I want you to notice, though, that it's actually impossible for me to put all 3 points on exactly the same line. I'm going to exclude one of them no matter what I do. So the goal here is to get something that is roughly a best fit line. So that's what we're going to go with. Now, once we have that best fit line, to determine its slope, we're now going to ignore these individual data points. They don't matter to us anymore. What we're interested in now is the trend that the line itself represents. Now, the easiest way to get a slope here is to look for a few places where the line goes directly through a meeting of the grid. That is, that this line and one of the vertical grid lines and one of the horizontal grid lines all meet up in one spot. And that's going to allow us to figure out what this line says the slope would be. Because you can see, since these don't all lie on an exactly straight line, if I took any two of them and calculated a slope, it would be different than what I've just drawn here. So upon looking at the data for a while and squinting at it, it looks like some of the best meetups seem to be up here. The next really good one I spot is over here at 3.6 cubic centimeters. So we can jot those down right now. This is, as we said, 10 cubic centimeters and 66 grams. This is 3.6 cubic centimeters and 24 grams. And so we know that the slope is going to be delta y over delta x, and so that will be 66 grams minus 24 grams over 10 cubic centimeters minus 3.6 cubic centimeters. And so that gives us 42 grams of change and 6.4 cubic centimeters of change. When we do the division, what we get here is 6.6 grams per cubic centimeter, which actually does match up with the individual data points reasonably well. But this gives us now the entire density based on a slope of a best fit line.